So recall that integers and natural numbers, they come equipped with the natural order. So you order these numbers with this less than equal to sign. And you can also think of topological spaces. They also come equipped with an order. So one space is contained within another space, as you can think of neighborhoods ordered by inclusion. So we can generalize this order here, this natural order, and call it a directed set. So a directed set is a non-empty set I. So you can always think of this I as integers or natural numbers. This comes equipped with the binary relation, less than equal to. So this relation is reflexive and transitive, just like in integers, and it has a property that for every pair of elements, so say pick up two elements A and B in I, then there is an upper bound. So there is a C in I with A is less than equal to C and B is less than equal to C. So in integers it is clear, you pick up any two numbers, say 2 and 5, then I can pick up a number 6. So 2 is less than equal to 6 and 5 is less than equal to 6. So if you have something like this, then you have this as a directed set, and this is the pre-order. So now you take a family of objects in some category, or you can think of it as groups, but these are indexed by this I. So this I here. So in general, we take this capital I to be integers. So you can have this family like this: A1, A2, A3, and so on. So if you're working in the category of groups, these are groups. So now once you have objects, you have to talk about morphisms. So if you have objects indexed by I, then you have morphisms. And if you're working in groups, we can say group homomorphisms like this. So Fij from Aj to Ai. So obviously say I is less than J. So this in a category will become this. And then we have morphisms. Now you have the contravariance. And that is what we have to notice. So this Fij corresponds to I less than equal to J. So arrow is going from J to I. So Aj to Ai. But I is less than equal to J. So this less than equal to becomes a arrow. So for example, 2 is less than equal to 3, then you can have morphism like this. Yes. So notice that this is this in a category. It becomes an arrow. So notice the contravariance. So now if you have three things, I, J, K, I is less than equal to J, which is less than equal to K, you have something like this diagram. Because of the transitivity, you have I is less than equal to K also. So these become a triangle like this. So obviously corresponding groups, these are AJ, AK, and AI. So notice we have just indexed it, and we are calling this here AI, this here AJ, AK. Just notice the contravariance. The arrows have reversed. So arrows have reversed. And this morphism here, we call it FJK just because of this order here. J is less than equal to K, so you can call it FJK. Here IJ, so Fij. Here IK, so Fik. So you have a convention for naming the arrows also. So you should have this commutativity. So that is the condition here. So this is nothing but this triangle. So first apply JK and then apply IJ. So first apply JK, IJ, that is same as Fik from here to here. So that is it. And obviously you should have an identity map FII for every AI. So this is the identity map. Obviously you have an identity map here, and you have an identity map here. So if you have these conditions, you have a directed set, and then you have these groups indexed by the directed set with these arrows which denote the contravariance, then you have this pair is called the inverse system over I. So now we can talk about inverse limit of such a system. So you take the inverse limit is nothing but a vector. So it is a vector of elements. So it is a subset of our direct product with a special relationship that this AI is equal to Fij Aj for I less than equal to j. So I is less than equal to j here. So this AI comes from some Aj here. So this lower index set AI, this element comes from some bigger element here. So that is the relationship. This Aj will get mapped to here. And this is more clear when we see example of p-adic numbers. And this inverse limit comes equipped with a natural projection, because this is a direct product. I mean, the simple example of direct product is Cartesian product. And if you have a Cartesian product, then you can obviously have projection map. So this is just, you can think of this like this: A0, A1, A2, and so on. It's kind of a big vector, and then you can project onto individual elements. This A0 comes from A0, this A1 comes from A1, this capital A2. So now you can project onto like this, and this satisfies the universal mapping property. So the fundamental example is of p-adic numbers. So p-adic integers we are going to consider here. So consider this sequence. So this AI lies in this field where p is prime. So you start with x0 is a0. So x1 is a0 plus a1p. So x0, so this a0 is the same, so therefore you can replace it with x0 a1p. Now x2, you copy this entire thing down here, but then you have plus a2p square, so additional term. So this is nothing but x1, so you write it x1 plus a2p square. So now x3, you have these three terms right here, and then you have additional term right here. So again, this is nothing but x2, so x2 plus a2p cube. So now you can see the relationship. If you modulo p this out, you get x0. If you modulo this p square out, you get x1. You modulo this p cube out, you get x2. So xn is like this, and you modulo pn out, you get xn minus 1. So again, everything, and then you adding additional term. So in general, xn is equivalent to xn minus 1 modulo pn, just like I have explained here. So this p-adic integer is a sequence of integers like this. You modulo this p, you get x0. You modulo this p, you get x1. Obviously, you can go from here to here by modulo p square. You get modulo p square, you get x1, then modulo p again. So obviously, if I modulo x2 p, so then this thing will go away, and you just are left with a0, which is x0. So this xn lies in here. For n less than equal to m, xm is equivalent to xn modulo pn plus 1. So obviously you're working with this inductively. So for example, you can go from x3 to x1 modulo p square. So if I do modulo p square, so this will go away, and obviously p cube also comes in the p square ideal. So these two will go away. But if these two go away, now look, this looks exactly like this. So I can go from x3 to x1, because 3 is greater or equal to 1. So 1 less than equal to 3. So now you can go from, so this is in 3. So from 3 you can go to 1 by just doing modulo p square. So that is it. So you have this big vector where elements next to each other are related. So here this is just modulo p, here this is just modulo p square. So you have x0, x1, x2, x3, and so on. So here you have modulo p, here you have modulo p square, and so on. So here you have modulo p cube. You can see it here. I've written it so that it is clear. So all these elements are related to each other. The second fundamental example of inverse limit comes from Galva extensions. So say you have this Galva extension, and then you can talk about finite Galva sub-extensions of omega. So these will form a directed set. So you can have this E0 is contained in E1, contained in E2, all the way to omega. So you can consider this omega as some infinite Galva extensions. So we are working for infinitary Galva extensions. So all these are sub extensions. They're all contained in omega, but they are organized by this increasing extensions. So obviously, you know, in Galois theory you have contravariance. So this is nothing but an arrow like this in the category. So rather than less than equal to, now you have inclusion map. So this you can think of as topological spaces ordered by inclusion. Now obviously Galois gives you contravariance. So if this is included, you have this. So E prime contains E, then you have this correspondence here which is in the opposite direction. So you have this direct system. Once you put Galois groups onto it, this becomes an inverse system. So once you have something like this, now you can talk about its inverse limit. So obviously this is an infinite extension. It contains all of these. So we have a restriction map because omega contains each one of these EIs. So obviously omega contains each one of these EIs. You can talk about the Galois groups. So Galois from omega to EI. So you have this restriction map for every I, which is given like this. This is same as what we have right here. So this thing is getting copied right here. So you can view this inverse limit as subgroup of, you're just taking all these extensions, and but these extensions are like a vector, and it consists of compatible elements, just like in p-adic numbers. So inverse limit is simply patching together all the compatible automorphisms of Galva extension of E into one big automorphism like this, omega over k. So the universal property of inverse limits will give us that this is nothing but an iso. So we are taking inverse limit over all these EIs. So that is it. So this omega contains this infinitely many sub extensions which keep on increasing. So in the end you will get omega. So in some sense omega is the limit of this increasing, but that limit is given as inverse limit right here. So this becomes an iso if you take an inverse limit.